Okay, so Jeff, that's all we have right now. So let's get started. So
Okay.
thank you everyone for coming to today's AIAA Las Vegas section meeting today on May 27th. We welcome you all. So now we'll introduce our section chair, Dr. Jeffrey Purcell. He is our section chair and is the AIAA fellow. He's a chief scientist in Raytheon. So welcome, Dr. Purcell.
Well, thank you very much, Ken. It's a pleasure to be here. We have another wonderful event this evening about the challenges of landing Perseverance on Mars by Al Chen from JPL. Roughly a month ago, we had another event with a talk related to Perseverance, related to it was also an award ceremony really for our section where we honored the teams at JPL with Perseverance, with the lander and the helicopter Ingenuity. They won the LA Las Vegas section Technical Award of the Year. We were very pleased to present it to them as part of a long history of very distinguished winners, including groups at UCLA, SpaceX, et cetera. So we're very pleased to recognize them then and to have this follow-on talk to talk about the challenges of the landing of Perseverance. But before we launch into that, we're going to continue our recognition series with recognizing our members with exceptionally long memberships in the Institute. And for that, I'm very pleased to introduce Aldo Martinez, our membership chair. So Aldo, please take it away.
Good afternoon, everyone. As mentioned before, I'm Aldo Martinez, and I am the section membership chair. And tonight, Ken, do you have the slide or do you want me to pull it up?
Oh, do you have? If you have, you can show. If not, I can show from my end.
Okay, I'll show. I'll pull it up from my end.
Okay.
Right. So. Can everyone see my screen?
Yep.
Yep. All right. So it is my pleasure to introduce some of the members who are celebrating their anniversaries. I know as early career folk, I know that I'm barely going to be coming into my 5 years with AIAA, but I'm had a pleasure of meeting a lot of members who've had 25, 40, 60, and recently I saw that there's some folks who have 70 years with this organization, and they have a lot to teach us, and I'm very grateful that they are always open to share their stories, share what AIAA has meant to them, and a lot of the experiences they gain. They definitely are what make this organization and aerospace industry as a whole the beauty that it is. And we always are tackling tough goals, such as reaching Mars, designing airplanes, or just trying to solve a lot of the toughest problems that we can face, right? And the members are what make those problems being able to be solved. And so it is my pleasure to give some time to the members who are present in this at this meeting, and those who weren't able to make it, and also giving them a little bit of recognition amongst all of the other all of the peers that are present today. More than anything, to thank them for their time. And if you guys want to come off mute and give a quick experience under 2 minutes of what AIAA has meant to you, or maybe something that you've encountered in your tenure with AIAA, we would be more than happy to give you the floor for a couple of minutes. But do be mindful that we do have a speaker coming up that I'm quite interested, and a lot of us are quite interested to hear the talk. So I will keep it moving. But without further ado, for the 25 years, we have Mr. Jason Pugsley. Please, I apologize if I misstate some of someone's name, feel free to correct me. I don't see Mr. Jason.
Mr. Pusley is not here.
Okay. Gary Rowley,
He's not here.
Dr. Paul Scott.
He's not here either.
All right, and for the 40 years, we have Miss Marlee Wheaton.
Meredith is not here, but we have Mr. Doug Ikemi. His short name is Harlock. He's also 40 years. Do you want him to say a few words?
Oh, sure, if he's more than willing to share some of experience.
Mr. Ikemi, please go ahead, say something.
Wow, I wasn't expecting to be on stage, but I guess you get a reward for surviving.
Yeah, I know aerospace is an up and down industry, but it's people like you who really make it worthwhile and kind of keep our hopes up and get us to the other side.
Mr. Ikemi, do you want to say a few words from your experience from Hughes or something? How did you join AIAA, something like that?
Well, back in my day, it was kind of a given. We would just sort of, from my grad school, we just kind of automatically signed up for ASME and AIAA, and actually everyone's good, but AIAA has managed to keep me engaged more, although I still maintain both memberships. And especially these days, grateful for the information feeds that you get via AIAA.
Completely agree. It is a quite of a mouthful sometimes when we say AIAA. But thank you for your service, and we hope to continue to provide that engagement and see you in future events.
Thank you.
All right, for 60 years, we have Dale Hoffman, Dr. William King, Dr. Muson Kwok, Mr. Fred Peitzman.
Yeah, Fred is here.
Hi.
That's right.
Hi, Fred.
Hi, it's Fred Peitzman.
Excuse me, sorry about that.
Well, people either spell or pronounce German names wrong because they're spelled crazy. It's great to be recognized for 60 years of AIAA. I actually started while I was at Iowa State College in the IAS, the Institute of Aeronautical Sciences, which merged with the American Rocket Society. I don't know, sometime around 60 years ago. I don't remember exactly when the two things merged. But I spent my whole career working for Northrop Aircraft, doing wind tunnel testing primarily. So I was there from 1961 through the end of 1994. And since then, I've been very involved with the Western Museum of Flight, the Aerospace Museum located in Torrance. Mm-hmm. And by the way, Al, we're really happy to have on loan from JPL a really nice 1/10 scale Voyager model that we're really happy to have on display. It's interesting to note that Dale Hoffman was also one of the people on the 60-year list. I know Dale really well. He also is involved with the Western Museum of Flight, so I see him very frequently. A really great guy. Retired as a vice president from primarily TRW. I think he worked for a while after it became part of Northrop Grumman. So anyway, I have some great recollections of early AIAA. One of the first things that I did when we got to California is we got to go on a field trip to the brand new International Theme Building at LAX. So that was a long time ago. And I've written a couple AIAA papers and so forth. So anyway, thank you very much for recognizing me, and look forward to some more good years.
Again, thank you for your service, and definitely look forward to seeing you in the future, and at least in the museum. I've gone there and can express the gratitude for being able to see some of the aircraft up close and talking to a lot of people like yourself. We also have Donald Reeves, Ernest Wade, and for the 70 years we have William Burks. I believe this was Jerry Elverum.
No, Bill is here.
Oh, Bill is here. I'm sorry.
Mr. Burks, go ahead. And Aldo, we have a 50 years, Dr. Roger Wagner. So don't forget about him after this.
All right. Bill, I'm going to ask you to unmute right now. I think you're muted at the moment.
How about now?
We can hear you loud and clear.
Okay. I like the previous speaker. I started as an AIS member and graduated to the AIAA. But the bulk of my career was with TRW. I was a mechanical systems engineer, and our main mission was developing various types of satellites for a variety of customers. And I can't really well talk about much of that, but I retired in 1992 and went to work for a private individual who had a patent rights to an analytical method for determining fatigue in metals. And we got an Air Force funding to develop that into a commercial product. And I worked for him for the better part of 12 years before we closed up shop. But once the recession hit in the early 19 teens, our customers who were state departments of transportation just refused to take any new technologies into consideration. So we used what funds we had, and we finally folded the doors of the company about 4 or 5 years ago. But that's about all. But I've been maintaining my membership in the AIAA. I don't go to meetings too often, but I keep in touch with a lot of my former workers at TRW, and I met a lot of good, interesting people at my following assignment. Now in my senior years, my wife and I just take care of each other and enjoy the beach. We live, fortunately, about 5 blocks from the Pacific Ocean. And right now we're entertaining one of our granddaughters and a friend. And later on this evening, my son who lives in Iowa and New York is coming to spend the next weekend with us. So anyway, I'm going to conclude now, and I will catch the Mars presentation at some later time. I'm going to join my family, but I appreciate you finding me and giving me the opportunity to speak up a little bit. So I'll sign off. Thank you very much. Bye-bye.
Have a good afternoon, and thank you for your service. And we also have Kenneth Goldman and Herbert Graham.
They're not here.
Ken, you mentioned someone was
Yes, Dr. Roger Wagner is 50 years membership anniversary. He's with us.
hello, Dr. Roger. Would you want to share some words?
Sure. Can everybody hear me?
Yes, we can.
Excellent. I'd say I started my career back at the University of Missouri many moons ago, and got a mechanical engineering degree then. And I was enrolled in the dual major, including aerospace. But that fell by the wayside. And so it was just the nature of the beast. Ended up transferring to Purdue, and I got my graduate work done there. And of course, the first job I had, I left it up to my wife at the time to choose East Coast or West Coast. East Coast was Grumman at the time. West Coast was Hughes and TRW. So she says, I want to go to the West Coast. I said, okay, and I'm going to pick the company. And I went with Hughes Aircraft. Thoroughly enjoyed my time there, and met a lot of dynamite people along my career path. And so, as Bill Burke stated, there's a lot I can talk about. There's a lot I can't talk about with some of the work that I've been involved with. But I've really gotten a lot of experience and satisfaction out of being an AIAA. So I will continue my effort here. And it's a shame to go out on a COVID note, but I want to get through this and put a few more years in before I say sayonara. Thank you very much for recognizing me.
Thank you, Dr. Wagner. And as always, it's our pleasure to build all these events up. And this is why we do it for the members, so that they can have some forum to express what they've experienced throughout their careers, and also to share it and gain some more knowledge. So without further ado, Ken, I'll hand over the presentation over.
Oh, thank you, Aldo. That's fantastic. So Jeff, that will is Alan's presentation. So you can go ahead.
Okay. Well, thank you, Aldo. Thank you, Ken. I'm very pleased to introduce our speaker for this evening, El Chen from JPL, who's going to talk about the challenges of landing Perseverance on Mars. El is a system engineer at JPL in the Entry, Descent, and Landing Systems and Advanced Technologies group. He's the Entry, Descent, and Landing lead for the Mars 2020 project. During his 10 years of duty on the Mars Science Lab, he was EDL operation lead, flight dynamics lead, co-led the Joint Science and Engineering Mars Atmospheric Characterization team, and also a member of the Flight Systems Engineering team. So he played multiple roles, multidisciplinary roles in this important mission. He also did the play-by-play commentary for the landing. I actually thought so. I thought I might have even recognized your voice. He also worked on the Mars Exploration Rovers project, performing EDL reconstruction and analysis and testing. So without further ado, El Chen, take away your talk.
Everybody, thanks for inviting me to come chat with you all. And congratulations to those of you who had big round number anniversaries in the AIAA. That's pretty awesome. I'm pretty impressed by you guys sticking through this, all of this. So I'm going to talk to you about the challenges of landing on Mars. Let me see if I can overcome the challenges of presenting on Zoom first. So give me a second to get set up here. Hopefully this will work. Oops, wrong presentation. Let's do this one instead. Okay, let me see if I can bring up the different things so I can make sure I can see you guys. Okay, hopefully you all are seeing my slides. I'm going to talk to you for a little while about the different challenges of landing on Mars and take you through the entry, descent, and landing system and how it worked on Mars for us a couple months ago. Feel free to yell out questions, I guess, or I guess you can't yell them out, but put them in chat and I'll try to take a look and see if I can get to them as we go, or we'll catch them at the end. I've got some video in here, so you don't have to hear me drone on for the entire time, and some pictures, hopefully, that maybe some of you have seen, some of you haven't. But hopefully I'll try to keep it a little fun and won't have to just be talking at you the whole time. So first things first, looking at the history of landing on Mars, the human race has had kind of a checkered history of success in terms of landing on Mars. I haven't updated this slide, of course, for the events of the last couple of weeks with the Chinese joining us in Utopia Planitia. But we're now better than a coin flip. We're on a pretty good roll, and the last few landings have gone pretty well, with Schiaparelli being the exception. But in general, landing on Mars has really been a challenge. It's been a difficult thing for us to accomplish as a human race, and we haven't really gotten better at it until kind of recently. As you can kind of see, a lot of these orange guys didn't have good fates, but the green ones have made it successfully, and some of them are still operating. So let's talk about what's challenging about landing on Mars. First things first, you gotta recognize the differences between Mars and Earth in itself. And one of them, of course, is the atmosphere itself. The atmosphere here on Earth is very thick, very useful for us for slowing down. Somebody once told me that Mars has just enough atmosphere to be really annoying. That's not quite true. We obviously need the atmosphere to slow down and use it quite a bit to land things on Mars. But it's got too much atmosphere to completely ignore. We want to use it to be able to land. But it's too little to really do the same kind of things we do here on Earth, like land capsules only using parachutes and things like that. In addition to that, it's got significant seasonal variability across the course of the Martian year. The atmosphere can change quite a bit. You get about 20% difference in density across the course of the year. And then also during parts of the year, you can get global planet encircling dust storms, which aren't great either. So the atmosphere is thick enough to support weather, clouds, and winds, but doesn't really have the same kind of thickness that we have here on Earth to really use it completely stop. In general, it's relatively poorly characterized. We don't have a lot of weather stations on Mars, though the number is growing, but nothing like we have here on Earth. So we're principally doing this based on orbiter measurements, remote sensing measurements of Mars, and then models to try to figure out what's going on. So that's kind of one of the first big challenges. The second big challenge, of course, with Mars is, as far as I know, there are no landing pads or runways that we can use. And then there's this conflict here between what we're trying to do there and where it's safe to land. Typically, we want places that look like runways or parking lots or landing pads, places that are flat, devoid of rocks, don't have slopes, don't have sand on them, things that are nice places to land. But the scientists who are pretty much driving the mission to some degree in terms of our objectives of these missions want to go to places with lots of rocks and steep slopes, places where we can access lots of parts of Mars's history easily. So those kind of things are in tension with each other. The science targets are landing hazards, and that's pretty much something we fought with all the way since the beginning of trying to land on Mars. And as we keep trying to get more and more aggressive with what we're trying to do scientifically there, we keep trying to go to harder and harder to places to land, where the terrain is really challenging us to find safe places to touch down. Finally, of course, because of those differences between Earth and Mars, testing and proving that the EDL system, or entry, descent, and landing systems, will work is a big challenge as well. There's always a mantra for us to test as you fly and fly as you test. But that's really something we can't do here on Earth for a Mars-type landing. The atmosphere is wrong, gravity is wrong, all sorts of things are wrong. So we can't really do a system test. Certainly couldn't do one affordably, and even if we could, wouldn't be very realistic. So in general, what we try to do to achieve that verification and validation to prove that our system is going to work is try to use systems that, as much as possible, are constrained so that they're something that we can analyze. And then we try to do testing of piecemeal testing of different pieces and build models from that, so that we can build models of the aerodynamic performance of the vehicle. We can build models of how the IMUs work or how the radars work, and then assemble them in simulation. So we kind of live in a world where we simulate as you fly and fly as you simulate. So if we stretch back to my MSL days, I figured I'd throw in an old video, but a good one, talking about the challenges of landing Curiosity on Mars. And I'll link that to why that's important to Perseverance in a little bit. But here you go, here's a quick video on that. This will play okay.
When people look at it, it looks crazy. That's a very natural thing. Sometimes when we look at it, it looks crazy. It is the result of reasoned engineering thought, but it still looks crazy. From the top of the atmosphere down to the surface, it takes us 7 minutes. It takes 14 minutes or so for the signal from the spacecraft to make it to Earth. That's how far Mars is away from us. So when we first get word that we've touched the top of the atmosphere, the vehicle has been alive or dead on the surface for at least 7 minutes.
Entry, descent, and landing, also known as EDL, is referred to as the 7 minutes of terror because we've got literally 7 minutes to get from the top of the atmosphere to the surface of Mars, going from 13,000 miles an hour to 0 in perfect sequence, perfect choreography, perfect timing, and the computer has to do it all by itself with no help from the ground. If any one thing doesn't work just right, it's game over.
We slam into the atmosphere and develop so much aerodynamic drag. Our heat shield, it heats up and it glows like the surface of the sun. 1,600 degrees.
During entry, the vehicle is not only slowing down violently through the atmosphere, but also we are guiding it like an airplane to be able to land in a very narrow constrained space. This is one of the biggest challenges that we're facing and one that we had never attempted on Mars.
Mars is actually really hard to slow down because it has just enough atmosphere that you have to deal with it. Otherwise, it will destroy your spacecraft. On the other hand, it doesn't have enough atmosphere to finish the job. We're still going about 1,000 miles an hour. So at that point, we use a parachute.
The parachute is the largest and strongest supersonic parachute that we've ever built to date. It has to be able to withstand 65,000 pounds of force, even though the parachute itself only weighs about 100 pounds.
When it opens up that fast, it's a neck-snapping 9 Gs.
At that point, we have to get that heat shield off. It's like a big lens cap blocking our view of the ground to the radar. The radar has to take just the right altitude and velocity measurements at just the right time, or the rest of the landing sequence won't work.
This big, huge parachute that we've got, it'll only slow us down to about 200 miles an hour. And that's not slow enough to land. So we have no choice, but we've got to cut it off and then come down in rockets. Once we turn those rocket motors on, if we don't do something, we're just going to smack right back into the parachute. So the first thing we do is make this really radical divert maneuver. We fly off to the side.
Diverting away from the parachute, killing our horizontal velocity and our vertical velocity, getting the rover moving straight up and down so it can look at the surface with its radar and see where we're going to land. And we head straight down to the bottom of a crater, right beside a 6-kilometer high mountain.
We can't get those rocket engines too close to the ground, because if we were to descend propulsively with our engines all the way to the ground, we would essentially create this massive dust cloud. That dust cloud could then go and land on the rover. It could damage mechanisms and it could damage instruments. So the way we solve that problem is by using the skycrane maneuver.
20 meters above the surface, we have to lower the rover below us on a tether that's 21 feet long, and then gently deposit it on its wheels on the surface.
As the rover touches down and is now on the ground, the descent stage is in a collision course with the rover. We must cut the bridle immediately and fly the descent stage to a safe distance from the rover.
So, of course, coming up on almost the 9th anniversary of the successful landing of Curiosity. That's kind of where the landing of Curiosity is really where the beginning of Mars 2020 began. Because the idea for Mars 2020 and the mission was to take that hard work, that 10 years of work we put into Curiosity, the Mars Science Laboratory mission, and then try to take that landing system that worked, that crazy landing system that worked that first time, and then try to use it again to start the sample return campaign. So the idea of Mars 2020 as a mission, when we first came up with it about 8 years ago or so, was basically to try to refly as much of that MSL system, that Mars Science Laboratory system that landed Curiosity as possible. In some cases, even some of the residual hardware we had left over from Curiosity, but to do a new mission, to land the first leg of a sample return mission to bring back samples from Mars. So the idea really was to leverage all that design and history from MSL to do this whole new mission. and then try not to change anything that we didn't have to change. Basically, given that all the blood, sweat, and tears we'd put into Curiosity and getting her there safely, let's leverage that again and not have to work too hard on those parts. So that was the idea. But what is this new mission that we were after? What is the mission that that Perseverance is doing right now? Really, it's about understanding the possibilities for past life on Mars. It's got these kind of twin objectives of understanding that the potential for ancient microbial life. We know that Mars itself was warm, wet, and habitable about 3.5 billion years ago, about the same time that Earth was warm, wet, and habitable at that time, and when life started to take hold here on Earth. So the idea really with that side of the mission, of the Perseverance mission, is to find samples that might have that evidence of past life and prepare it for return to Earth by caching them in tubes that we can then take all the way back from Mars back to Earth. A secondary objective, of course, is to prepare for eventual human exploration of Mars. So we have things like the MOXIE instrument that you might have heard about recently that is trying to take some of that carbon dioxide atmosphere of Mars and turn it to oxygen, which we've already done successfully. We're also carrying other things like spacesuit materials to see what happens to them over time on Mars. Again, with the idea of eventually preparing for humans to land on Mars. But with that first kind of astrobiological goal of going to the places where there might be evidence of past life, we want to make sure that we can go to the places that both had that past life or might have had that past life in the past, and then it's still preserved for us to find now. Places like Jezero Crater. Jezero Crater, which is the site that Perseverance is at now, is believed to have once been a lake. You can kind of see from space, and I'll show you some pictures from now, you can see how the an inflow channel kind of came into the crater, which then had a lake there and deposited a delta there. And then there's an outflow channel as well. Scientists once told me that there's no delta on Earth that you can't find the signs of life in. So that's kind of what kind of drove the idea of going to Jezero now, there is a delta there now that we can still see, even though all that water is gone and the surface of Mars is dry and desiccated and cold. We can still see that delta that's formed there. And hopefully that delta is a good place to preserve those signs of past life. But that it's in itself provides a challenge for us that we'll talk about a little bit later, in that deltas and this crater are not the parking lots and landing strips that we're looking for. So let's talk a little bit about the Mars 2020 entry descent landing system, again, borrowing heavily from the Curiosity landing system. The idea and the kind of ethos behind what we're doing was to keep as much of the Mars Science Laboratory design as possible, but fix things that didn't work quite right for us on Curiosity, although we landed successfully. We did find some things that didn't quite work right. Or things that weren't very robust, things that we might have gotten away with last time that we don't want to take our chances with again. We have a much bigger rover here this time. Perseverance itself is about 130 kilos heavier than the 900 kilo Curiosity rover, so we have to land that bigger rover as well at more dangerous sites, places like Jezero, but without breaking that heritage architecture that we have from Curiosity. And of course, kind of looming over us in the last year or so, of course, was the pandemic itself. Where just like we're talking here on Zoom instead of together in person, we ended up having to finish the build of the spacecraft remotely, launch it in many cases remotely, and then operate it in a lot of cases from places like my guest bedroom. So that was an additional challenge that we didn't see coming. Going back to MSL and taking a look at what went wrong, there's nothing like trying to do something again to realize what didn't go quite right the first time. One thing we noticed about the landing of Curiosity is that we actually touched down slower than we had intended. Curiosity and Perseverance both are intended to touch down at 0.75 meters per second. And Curiosity, after a detailed reconstruction, actually touched down at about 0.6 meters per second or so slower than we had intended. That actually turned out to be an issue with gravity. You think you know gravity pretty well at different places, even like Mars. But at a place like Gale Crater, which is this giant crater that's very deep but has this big mountain in it, we had the local gravity modeled incorrectly for that site. And because we were only using 2 of our radar beams during that sky crane maneuver, we were kind of assuming we knew what the gravitational acceleration was, and we were wrong. So then to correct that for Mars 2020, we've created high fidelity gravitational models for all of our sites that are kind of hyper-local. We're using the terrain and the shape of the terrain and assumptions about the density to produce a terrain implied gravity model for each of our landing sites that we were choosing between, and of course for the Jezero site that we eventually went to. Second, on the parachute deployment side of things, one thing we noticed after taking a look at at all of our navigational data and of course the IMU measurements from the Curiosity landing itself, we noticed that the parachute deployment event, which is quite violent, we've got a parachute that we're firing out of the back of the vehicle with a mortar, basically a cannon, was causing a bunch of ringing in our panels and then in the IMU as well, causing a navigational disturbance. This is kind of similar, right? We're getting rates that we were seeing at the IMU, which led us to think about what happened to Schiaparelli to some degree. Schiaparelli was lost due to higher than expected rates detected at the IMU as well, that caused saturation of the vehicle, or saturation of the inertial measurement units. So to be sure that that didn't happen for us, we kind of softened up the parachute train a little bit to reduce the disturbance. And also developed a way to reduce the resolution of the GNC filters in the IMU so that saturation wouldn't occur. Finally, on another project that was around the low density supersonic decelerators project that was around to develop additional aero decelerators for Mars, they were developing a large parachute that was going to be hopefully used for future missions even bigger than what became the Perseverance mission. And they were designing that parachute in much the same way that we've been designing parachutes and testing them since Pathfinder and Mars exploration rovers and Phoenix. This approach where we had been designing the parachutes and then testing them subsonically. But they went as far as testing them supersonically, which led to something that I'll show you here on this next video. Hopefully this will play too. Shut off my video for bandwidth. So this is over the skies of over the Pacific, out over the Pacific Test Range in Kauai. What you're first seeing here is actually a balut. That's a different kind of decelerator, but it's used to stage this much larger parachute that, again, we designed in much the same way that we've designed all our parachutes for Mars since Pathfinder. There's that balut pulling out the parachute, and there goes that parachute. Let me play that one more time because it's the stuff of my nightmares here. Of course, we have to test parachutes. We have to test them up in the upper atmosphere to get the Mach and density about right for Mars. So these parachute tests are occurring upwards of 100,000 feet above the surface and going around Mach 2 or so. So that parachute exploding there and turning into a confetti machine really gave us some pause. Given that we'd been testing and designing these parachutes the same way, the question kind of came to our mind here. You know, have we been getting lucky? Is this something that we've been edging closer to the edge of this cliff here, and then we finally stepped over it with this parachute? You know, have all these parachutes that have been working on Mars really just been a function of us not having, you know, rolling the dice and coming up and winning every time? So to make sure that that wouldn't happen again for Perseverance, we made the difficult choice to actually strengthen our parachute, to change the design that had just worked for Curiosity for a system very similar to ours. And we decided to strengthen it. We decided to increase the strength of the broadcloth and strengthen up the lines as well. But we weren't satisfied with that alone. We wanted to be sure that we could prove that we could that these would work supersonically. And supersonic testing really, aside from this low density supersonic decelerators test of parachutes, was not something we'd done for Mars since the Viking era, since the 70s or so. So we had to, of course, also resurrect the ability to do these types of tests, and perhaps do them in a different way than we did with the low density supersonic accelerators test. So we actually did that by going to the Wallops Flight Facility and launching our parachutes on sounding rockets out over the Atlantic Ocean. So as you see this rocket right before, I'll show you the video of it launching here, in that purple test section is a parachute facing out the back, our redesigned parachute, and we're going to take it up to that 120,000 feet or so and deploy it around Mach 2 to demonstrate that this new supersonic parachute will survive that violent inflation, that less than a second inflation that we see and expect on Mars. So here's a little video of it on the way up. You can get a sense of how high we are up here in this video of the parachute inflating here. Don't blink or you're going to miss the parachute inflating. As I said, inflations on Mars are about 0.6, 0.7 seconds for our 21.5 meter diameter parachute. And here on Earth, they're even shorter. So. So we were able to redesign our supersonic parachute and then test it supersonically here on Earth. You can see the limit of the Earth and get an idea of how high up we are. In case you want to see that in slow motion, I've got a little slow motion video of that too. I think we've got some time. So, oops, too far. Let me hit play on that. Here you go with things massively slowed down. You can see the pack coming out there and all the lines being pulled out of the pack here as it is getting out to line stretch out here. You can see these parachute inflations are really violent given how quickly they occur up here in these kind of conditions at supersonic speeds and these rarefied conditions in the upper atmosphere. But this is what we expect and then did see on Mars. You can see here how we're about to develop basically all the load as the parachute begins to inflate. And the ways it inflates, how many lobes that do we develop on the way out there can be pretty chaotic from one inflation to the next. But this is a pretty close to picture perfect inflation there. And this vehicle saw, or this parachute saw, in the neighborhood of 50,000 pounds of load during this test. So good, we made the parachute more robust. Hopefully we stepped away from the cliff of what we'd been doing and wouldn't have a bad day with the parachute. So let's move on to kind of other challenges here. I can start my video again so you can see me talking to you. 2020 itself is one thing that happened to, timing is everything, they say, right? And the 2020 opportunity happened to be a great time to go to Mars. I told you a little bit about the pressure cycle, right? And the fact that the atmosphere of Mars changes from season to season. That's principally driven by the orbit of Mars. Mars's orbit is a little bit more eccentric than that of Earth's. So as the planet gets closer to the sun, more of the atmosphere goes from being stuck in the polar ice caps, that carbon dioxide stuck in those polar caps, and gets released in the atmosphere. And it's much more useful for the atmosphere for folks like me who are trying to land things, because once the carbon dioxide molecules are in the atmosphere, we can use them to slow down. Another thing about the 2020 opportunity in particular is it's not quite as close to the sun as you could be. And as a result, we don't get the kind of energetic global encircling dust storms. We're not really in that season. During this part of the year, the atmosphere is reasonably thick with the carbon dioxide molecules in it, but doesn't have the threat of these planet encircling dust storms, which has been great. So that kind of gave us, just by launching in this opportunity and landing in February of 2021, more stopping power, more atmospheric molecules to use, which basically allowed us to land a bigger rover at no cost. We didn't have to do much to the design. We just had to arrive at the right season. Whereas Curiosity, the MSL mission, actually landed on Mars kind of at the worst time of year, when all of those molecules of CO2 were trapped in the polar caps instead of being in the atmosphere for us to use. So just by going in this opportunity, we basically got those 130 kilos of extra rover that we had to deliver for free. So now let's talk about the terrain, specifically at Jezero Crater. If you look on the left here, we have a picture of the Jezero Delta, where we were headed from the Mars Reconnaissance Orbiter. There's some false color there to indicate kind of all the different minerals, especially those that are kind of modified by water, places where we know that there was water based on the chemistry of the minerals we're seeing. But what you might notice here is that there's really no flat spots. And even the spots that look flat in this picture have lots of rocks on them. In fact, our version of what you see on the left is on the right. This is our hazard map, which is kind of coloring things that are dangerous to land on, either because we can't touch down on them safely. There's tons of rocks. You kind of see those kind of splotches to the east. Those are all rock fields. You can obviously see the edge of the delta. Those are high slope places, things we don't want to land on. And then there are other things like that crater that's kind of in the middle of the delta, and some other places that are places that the rover might actually be able to successfully touch down on, but we wouldn't be able to drive out of. So we didn't want to treat places that we could land on but not do the mission as safe either. So we marked those as death as well. And there's a lot of red here, right? There's not big splotches of area that we can land on that are safe. We contrast this to past missions where basically the landing ellipse, the air ellipse where we can come down and touch down, had to be basically free of hazards. And here we have hazards all over the place. So how could we land at a place like this? What did we have to do to our system? And in fact, Jezero itself was proposed for the Mars Science Laboratory mission for Curiosity, but was rejected because of maps like this, because it was too dangerous a place for us to land. So we had to add some tricks to our system here to be able to go to a site like this safely. The first thing we added was something called range trigger. So range trigger allows us to deploy that supersonic parachute based on navigated range, as opposed to just navigated velocity. For Curiosity, as it was coming in, when it was slowing down on the capsule, it was deploying its parachute based on hitting a particular velocity. When you get to that targeted velocity, deploy the parachute and slow down. And in fact, it knew from its navigational filter that it was actually a little bit past where we had wanted to deploy the parachute, but it was dutifully doing what we asked it to, which was deploy based on getting to a safe velocity. But we changed things up a little bit for Mars 2020 to be able to shrink our landing ellipse, that space where we can land on the ground, where we might end up, by having the ability to deploy that parachute based on where the vehicle actually was. So that took our landing ellipse that for Curiosity was around 25 by 20 or so, to eventually getting down to a ellipse that was about 7.5 kilometers by 6.5 kilometers by the end, by the time of about launch or so. So you kind of see that really shrinks down especially the major axis of our landing ellipse, allowing us to fit that landing ellipse in tighter spots, like that Jezero crater area, and target the delta where we eventually touched down. The second and most probably even more important piece of the puzzle was terrain relative navigation. Here you see kind of the timeline from Curiosity of our touchdown, from heat shield separation at about 8 kilometers, to priming the engines that we used to slow down at about 3 kilometers, to doing that backshell separation that was talked about during the video at 2 kilometers, and then doing that powered flight down to the sky crane. So without wanting to change kind of what was happening on the vehicle, because we wanted to live within the Curiosity architecture, we needed to add a system here, this terrain relative navigation system, without disturbing that. So the first thing we wanted to do was add something we call the lander vision system. So after that heat shield comes off, with terrain relative navigation, we were taking pictures of the ground and using those pictures to match them up with an onboard map from the Mars Reconnaissance Orbiter. I don't know if people do this anymore, but it's kind of like looking out the window of your car while you're driving around and then holding your map there, and trying to figure out what you see out the window and match that up with your map and thereby figure out where you are. That's what we were asking the vehicle to do too. So really what that lander vision system did while on parachute during a time when things were relatively quiescent on the vehicle, and we were just descending and waiting for backshell separation, we took those pictures, matched them up with an onboard map, and figured out where we were. And then we could use that information once we separated from the backshell to smartly fly the spacecraft with a safe target selection, divert. So instead of just diverting to avoid the backshell, we diverted to avoid the backshell, slow down, and head for the nearest safe site. So what that allows us to do really is to target tiny little parking lots that are scattered around the landing site instead of having the whole place be one giant flat place. So that really gives us the ability to allow some of those hazards that you saw in the hazard map earlier to actually be at our landing site, because with the knowledge that we have the ability to fly to safe spots that are in between those hazards. So that kind of opened up the world for us to sites like Jezero, where there are hazards throughout the site, but there are enough safe spots nearby to allow us to touch down. Okay, and I've got, I think, a little video, hopefully this will play okay, about terrain relative navigation.
We are in Death Valley testing terrain relative navigation, the new technology for Mars 2020. The terrain in Death Valley is very much like Mars. It has a lot of sand dunes and steep slopes. It's quite similar to the landing site that Mars 2020 will be going to. We're taking a copy of the system that will be on the spacecraft, and we're testing it in the way that it would be used during the flight mission.
Terrain relative navigation gives the vehicle the ability to figure out where it is. This is kind of along the same lines of what the Apollo astronauts did with people in the loop back in the day. Those guys were looking out the window and looking for different craters and other features on the moon that they knew of from the maps we had of the moon. So that way they could figure out where they are and figure out where they needed to land to be safe. So for the first time here on Mars, we're automating that.
What terrain relative navigation gives you is the ability to avoid hazards that you already know about. So large hazards, hills, craters, things that you've seen before. With the camera, we take images as we're descending, and we match pieces of the image to orbital imagery that we have stored on board. And if we make many of these matches, we're able to figure out where we are relative to the map.
If we didn't have terrain relative navigation, the probability of landing safely at Jezero Crater is about 80 to 85%. But with Mars 2020, we can actually bring that probability of success of landing safely at Jezero Crater all the way up to 99% safe every single time.
We don't have an astronaut that we can put on board Mars 2020, but we can put this system, this terrain relative navigation system, so that the spacecraft can figure it out on its own.
I could see it being used on lunar missions, science missions, as well as human missions. Future Mars missions, of course, Mars sample return, Europa lander, landing on a comet, pretty much everywhere you want to land. You're going to want to have terrain relative navigation.
Okay, so with the addition of range trigger and terrain relative navigation, we felt comfortable going to a site like Jezero. So we ended up with an entry, set, and landing timeline that kind of looked like this. We've got that 7 minutes of terror again here, going from the top of the atmosphere to the bottom. But now with the introduction of range trigger, deploying that parachute smartly at the right place, and of course terrain relative navigation happening after heat shield separation, and once we have a radar lock on the ground. Shortly before backshell separation, and then using that information to fly to a safe spot nearby. And that's what happened on February 18th. So let me show that video to you as well.
Propulsion, go. EDL phase lead, go.
We have deemed Perseverance ready to execute entry, descent, and landing on her own.
Confirmation of entry interface. Perseverance is currently going 5.3 kilometers per second, about 120 kilometers from the surface of Mars. It will start controlling its path to the landing target. Parachute has deployed and we are seeing significant deceleration. The heat shield has been separated. Perseverance now has radar lock on the ground. The backshell has separated. Skycam maneuver has started, about 20 meters off the surface.
Tango Delta, nominal.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the sands of past life.
Forgot to mention, but you might have seen as part of that video, some of our video from the new entry, descent, and landing camera system that we had on there as well. So for the first time, we got to see a parachute inflate on Mars, and got to see some other things like the descent stage lowering down the rover, and of course the rover being lowered from the descent stage. That picture was on the front page of my presentation here. So of course, that's how things went in February, but how did it go from a technical perspective? Well, we're still working on the reconstruction of the full trajectory and everything that happened during landing, but we have a pretty good idea right now how things went. In general, things went pretty much as we expected. If you take a look at this this figure here, this timeline, I've updated it with things that are in green are things that went pretty much as we expected within 1 sigma of our prediction. Things in yellow are 1 to 2 sigma, and then things in red, just the one thing, were a bit of surprise. In general, things went pretty well. We had the timeline almost perfect. We ended up with 6 minutes and 59 seconds from entry to touchdown. So 1 less second of terror than we expected. In general, the altitudes of things were a little bit higher than we expected. Those are the 2 yellows that you kind of see with parachute deploy and heat shield separation, mostly because the atmosphere was a little bit different than we expected. not necessarily surprising, but since it's hard to really predict the weather on a different planet at a given time in a given place, but still pretty close to what we had intended. The only real surprise really was that the entry deceleration was a little bit lower than we expected. Again, we're still figuring out what's going on there, but we think it's related to the upper atmosphere being thicker than we expected. So let's talk about where we ended up on the ground. If we take a look at how that range trigger performed in terms of deploying the parachute and where we ended up at backshell separation, we ended up at about 1 sigma or so from the center of our kind of landing ellipse where we had targeted. So again, well within expectation and only about 1 kilometer from where we had targeted the whole system to go to. So things went pretty well there. Let's talk about terrain relative navigation. The terrain relative navigation system itself worked very well. It took us down to a place that turns out to be very safe. And the lander vision system, the part that helped us figure out where we were, locked up pretty much immediately. It went to it got a solution pretty much as soon as it could, as early as it could, based on the images, and found us a nice safe spot. If you take a look at this, hopefully you can see my pointer here, this video up here on the top right, let me walk you through what we're seeing here. The top right picture, or the images that you'll see there, are actually the images from the lander vision system camera. It's a little bit dark. That's actually sort of basically intentional because it's easier to underexpose pictures and then pull information out of it than to have things blown out and saturated and try to figure out what you're seeing in there. So that's what the camera itself was seeing on the way down. This picture down here is kind of the full 30 kilometer by 30 kilometer map. I told you there's an onboard map that we're matching up the pictures that we're taking to that map. And then this blue area is kind of the cropped map. It's the part of the map that we believe that we're in, and that's what you see over here blown up. The red area is the field of view of the lander vision system camera. And then the green squares that you'll see and the multicolor squares that you see are the landmark matches, the kind of things that the lander vision system has identified and matched up with what's on the map. So I'll play that and you'll kind of see all the images that are taken from the time that the lander vision system is initialized all the way through backshell separation, and then past that, actually, we went ahead and left it on during powered flight just to see how it would do at lower altitudes, even though we were no longer using that information. So here you can see that it jumps right away to having identifying lots of landmarks. It goes from that coarse mode to a fine mode. That really gives us the higher precision that we want to have later on. You can see as we down there that we have plenty of landmarks. We pretty much saturated our system with how many landmarks it could find. So it did a real good job identifying what it saw in the picture versus what we saw in real life. In the end, we ended up touching down only about 5 meters from the site that was targeted by the safe target selection system. So that tells us that the whole system performed very well, that the accuracy of the lander vision system was very good, and our ability to fly to and target and fly to a site using the engines during powered flight was also very good. And it turns out this was pretty important to us. If we had done a divert much more like Curiosity had done with the Mars Science Laboratory mission, we would have ended up diverting to a site that would have been about, to a landing spot that would have been about 20% hazardous. So a 20% chance of death at touchdown. So it was very important that we chose to use the terrain relative navigation system here to fly to Jezero, or we would have had a pretty bad day if we tried it without it. You can kind of see here where we landed in the pictures down here at the place we've deemed Butler Landing, that it's a nice little safe oasis there, a blue oasis amongst hazards all around it. So this turned out to be a great place to land. Okay. So let's move on. Let's talk a little bit about why we landed where we landed. So you saw that the target of the ellipse was kind of closer to the edge of the delta, the edge of that cliff. We really wanted to land as close to the delta as possible. But it seems likely, again, due to that atmosphere probably being a little thicker than we expected, causing the parachute deploy altitude to be a bit high, plus some combination of not getting the winds quite right at this site, again, trying to predict the weather at a place that we've never been to. The backshell separation point was about 1 kilometer long of the landing ellipse. Then in addition to that, the safe target selection system works by kind of considering a couple different areas where it could land and picking the safest one. The places that it was choosing between are kind of shown in this bottom right picture. In the upper wedge, we had this black spot, which was closer to the original target of the full landing ellipse. But we actually chose this white square in the bottom right because it was a bit safer. It was about 1.3% chance of touchdown hazard versus 1.9% chance of a touchdown problem. So we diverted to that safer spot. So that was about an additional 600 meters or so away from the center of the landing ellipse. So that kind of took us a little bit further away from, what we would have called the bullseye, but still not too far away, only 1.7 kilometers long of the center of the ellipse. Okay. So let's take a look at how we did, in terms of the simulate as you fly and fly as you simulate. Using some of those videos that we took from those entry, descent, and landing camera systems. So here, what we have is a view of the rover from the descent stage looking down on the left. So that's the actual flight video. And then on the right, our Adams simulation of what was happening there, where we buried kind of the mechanical behavior of the vehicle, as well as the guidance, navigation, and control aspects. So the flight software is also mimicked in that Skycrane simulation. I can try to play that again real quick. Maybe I'll play again so you kind of get an idea of how well we modeled that. Or maybe I'll try to play it. Oops. There we go. I don't know about you, but this turned out to look pretty good to us. What we actually got to see in real life, which was kind of not mind-bending to finally see what it looks like to land on Mars, pretty much matched up with what we had from our simulations. We also did the reverse, tried to take a look from the rover looking up at the descent stage, both in the flight camera video and then with our simulation as well. So hopefully this will play. There you go. Not quite perfect, but pretty much got the behavior pretty close to right, I think. There it is. I think if those of you who've been following the mission know, we've deployed our little friend there, the Ingenuity helicopter, which just completed its fairly eventful 6th flight not that long ago. But here's a picture from the ground there, of course, of right after deployment of the rover taking a selfie there with Ingenuity sitting right next to it. So just to close out things, you might have seen the pattern on the parachute being a little bit different than the one we tested. Those of you who are following along know that in binary on that parachute, we left ourselves a little message and a message for the world, kind of, our own little unofficial motto at JPL with Dare Mighty Things written there in the parachute, and then with the latitude and longitude of the Jet Propulsion Laboratory as well. And of course, Dare Mighty Things references the speech by Theodore Roosevelt, who's I put the quote right here. But I feel like it's a good reminder for us to never be afraid to take chances, right? To understand both failure and success, so we really understand what failure feels like when we have it, and that we're not afraid to really stick our necks out there and take chances for the chance to have a great victory. So that's about it. I guess this is when I could take questions. Let me stop sharing so I can figure out how to find the Q&A box.
Oh, so Al, it's time for Q&A.
Mm-hmm.
Okay, Jeff, do you want to say something?
I want to thank Al for his excellent talk. I enjoyed the videos, especially the ones I hadn't seen before. There were a few, so that was wonderful. Congratulations again on the success of this mission. Go ahead, Ken. Let's have some questions and answers.
Okay. So thank you. So Mr. I think Patrick has a question. Let me see, Patrick. Patrick, go ahead. Mr. Kransek.
There's a lot of mute buttons. Sorry, just got them all turned off. So my name is Patrick Klansik, and I just started my space career in 2012. Diverse background, but watching the 7 minutes of Terror Descent live feed for NASA JPL was what helped me as the catalyst to embrace my new professional phase, being in space. And I've been thrilled and excited for it ever since. So diving deeper and deeper all the time. I want to thank Al Chen also for this presentation. My question is relative to, can you describe the process at arriving or for arriving at the terrain relative navigation system solution? In other words, was it the availability of new technology? Was it working a creative solution to drive technology? It seems like a real dynamic balancing of risk reduction in parallel with enhanced mission parameters, more precise landing zone. So what does JPL use as an approach, generalized solution methodology, problem-solving methodology, to come up with a solution like that terrain relative navigation? I mean, it's phenomenal what it does. How did you work through getting there? How does JPL do that? What is the team's process?
That's a great question. There's a lot to unpack there. I think the key thing for me really is that this isn't something that we just kind of came up with and then decided to fly, right? This is a technology that's been in development for like 20 years for us. Some of the folks that put terrain relative navigation or helped us put it on Mars 2020 have been working on it for a lot of their careers. And in fact, the DIMES descent image motion estimation system on MER is kind of like a grandfather in some sense of what we eventually flew on Perseverance. The ability to identify landmarks on the ground and to use them to track them from image to image is a piece of this that is 20 years old, if not a little bit more than that, if you want to go back into the research aspects of it. So it was key for us to have a technology development program going along the sides. Even while we were doing Curiosity, we were working on this technology that we would need, that we would know we would eventually need, and then it was ready for us to infuse for Mars 2020. So we got it there to the right level of maturity that was about the right point after Curiosity landed to finally take a chance on adding this kind of new groundbreaking capability for us to go to these types of sites.
Thank you. I appreciate that. It's a 20-year process is what I take away, and keep doing development, right? Looking 20
Absolutely.
years into the future. What's the next thing JPL is working on that'll happen in 20 years? Love to hear about that some other day.
All right. Looks like there's a couple of questions in the Q&A that I could take, I guess.
Alan is add to Mr.
Yeah,
Chan.
hello.
Oh, hello.
Hi, my name's Alan as well.
They like your name.
Yeah. So how does the hazard percentage on the map get determined? I guess it's determined primarily on flatness, or I assume, there's also some human input as to, where not to land, right?
Yeah, excellent question. That's a great thing to bring up, because I think that's kind of one of the key features of the way we flew terrain relative navigation, is that we didn't ask the vehicle to determine what a hazard was on the fly, right? We figured it out on the ground.
Right.
So we made the job a lot easier, right? We don't have to have the vehicle have to think through what it sees and then identify hazards. We gave it a hazard map and a list of places to go. So how do we do that, right? There are a lot of different things that are hazards to the vehicle. Primarily, the rocks, of course, is a big one. Identifying rocks that are big enough that we can't land on them. There are certain rocks, of course, that we have enough ground clearance to land on, and those aren't hazards. But we wanted to be sure that we could see or identify all the rocks that are possible. But even with that, there's challenges. The Mars Reconnaissance Orbiter can't quite see all the rocks that are hazardous to the rover. So we kind of had to, in addition to the ones we could see, we had to model additional rocks that were smaller than the ones we could see. So that's kind of on the rocks end of things. Slopes themselves are sometimes problematic, although the vehicle is very good at dealing with slopes for the most part, because we're using that mobility system, which is designed to drive around and deal with Mars terrain as a touchdown, as a landing gear. Still, things that are too steep, like the edges of that delta, which are basically cliff walls, are no good to land on either. So we created digital elevation maps using, again, images from the Mars Reconnaissance Orbiter to help us create a slope map of the entire landing ellipse where we could come down. So we could identify which places were too slopey, right, too steep to touch down. Finally, I talked about the fact that there are some craters there that are filled in with things, and there's also these sandy areas with lots of polygonal ripple fields or other things that are difficult for the rover to drive on. We wanted to mark those as hazards as well, because we didn't want to touch down at a place where the rover wouldn't be able to accomplish the mission. If you touch down successfully but can't drive away, that's still a failure. So we marked those as well on our hazard map that we gave to the vehicle to fly to the safe spots. So slopes, rocks, and bad places to drive are pretty much the major hazards that we were trying to avoid.
Very cool. Thanks. How big is the hard drive or SD drive on the Perseverance?
Depends which one you're talking about, right? The ironically, the EDL camera system carries. We ended up with a new computer to do the lander vision system part of this, the terrain relative navigation. But all of that is dwarfed, ironically, by the commercial off-the-shelf EDL camera system and all the data we collected there. So there's not much in terms of what's on the computer in terms of the main thing flying EDL. It's surprisingly dwarfed by this off-the-shelf camera system that we have on there.
Pretty cool. Thanks.
Okay, next is Aaron. Aaron, do you want to speak out? Aaron, I think you posed a question. Do you want to speak out your question? You raised hand as well.
Can Aaron talk? Is he still in the attending list or?
No,
hello, am I unmuted?
Oh, there you go.
Okay. Yes, this is Jacob. Actually, this is my wife's Zoom account. But my question is during. I watched one of the Perseverance live streams for EDL, and during that live stream, I remember hearing some of the the comms chatter right after touchdown, referencing Monte Carlo sets, either being started or being aborted or that type of thing. And I'm curious if you could speak a little bit about the types of Monte Carlos that were being run, right during the EDL and then immediately during and after touchdown. It seems like kind of an odd time to be running that sort of analysis.
Yeah, good question. So as we're getting closer to Mars, our uncertainty in where we are prior to hitting the top of the atmosphere is shrinking very quickly. And that solution can move a bit. It's kind of like as you follow into the gravity well of Mars, you get the idea of really where you ended up. So that was very perceptive of you. We were running Monte Carlos throughout EDL because we were grabbing the last kind of known position based on radiometric navigation as we got closer to Mars to kind of recalibrate where we thought we might come down and what the performance of the vehicle might be like. So you're right. You were hearing us talking about Monte Carlo runs. They're all based on the latest navigation solutions that we were still getting from interplanetary nav.
Okay, yeah, thank you. That's very interesting. I imagine that you must have a great automated process for reducing that data and presenting it and making it actionable as it's being run. Having done some Monte Carlos myself, that's a difficult part of the process.
Yeah, I mean, it's too late to do anything about it, of course, but at least it gives you an idea of what to expect. In case there are any surprises there.
Thank you.
Okay, next is Mr. Robert Baker. Bob, speak out.
Did you have to use any machine learning in the process that you used?
That's a great question. So we did use some machine learning actually to help us try to identify both additional rocks that we couldn't see and to try to smartly identify certain types of terrain that might be problematic. So we did use some machine learning on the terrain identification side of things. Not, of course, on board the vehicle, but in terms of characterizing the hazards here on the ground.
Did it help?
Yeah, I think so. I mean, it certainly made the job a little bit easier, and then we could cross-check it with human checking to some degree. But there's still a lot of terrain to look at, even with a much smaller landing ellipse than in the past.
Okay, the next question is from Guido. Guido, do you want to speak out? Guido is our member whom I mentioned. He has over 70 years of AIAA membership. It's amazing. So Guido.
Yeah, the Chinese have announced that they've placed spacecraft on Mars. How much do we know about their spacecraft and what similarities and dissimilarities do they have, and the level of technology?
I don't personally know much about it. I mean, I've seen some things that have been written about it, and that leverages pretty heavily what they did for the moon, which has been quite impressive. I know that the rover itself is about a third the size of a third of the weight. It's kind of big because of solar rays, but about a third the weight of Perseverance or so. It's in that neighborhood between a third and half. And they went to Utopia Planitia, which of course is a nice flat place to land, a good place to head if you want to be free of a lot of hazards, which is great. But I don't know too much personally about it.
Okay. So next, Randall. So Randall, do you want to speak out your questions, or you? Basically, he has a question: how many frames per second are processed by the TRN system?
Great question. We process one image per second. We don't need to do it too fast because all we need is to know where we are, and then we use that information. We can propagate that with the rest of the navigation filter really to figure out where we are and then decide where to go.
The next question is from Mr. Holger Iceberg. Holger, go ahead.
Oh yeah, thank you. I was wondering if the sky crane was really test flown on Earth, or was all physical data really only based on Viking lander experiments?
So as a system, yeah, so that's a good question. As a system, the sky crane really can't really be tested very easily on Earth, given that everything's kind of wrong, especially gravity. So we've tested things in pieces, right? We've tested the engines themselves and characterized their performance so that we could model them and assemble it in simulation. Same thing with the deployment of things like the mobility and the deployment of the rover below a structure. So we got a good idea of how the bridle umbilical and DRL, those kind of wires that connect the descent stage and the rover together and how that works. But you can't really do a full system test of it here on Earth.
Okay, so if that's the next question is from Mike. Mike, go ahead.
Yeah, hi, Al. I really enjoyed your presentation, and I'm glad to be able to speak to you. I was able to join a AIAA viewing party during the landing. Actually, I was on with AIAA the section with Ken, so it was nice. The question is, what happens to the flyaway after it flies away from the vehicle? Does it have any purpose after that?
Good question. So the descent stage flew away to the northwest about 600 meters and crashed into the ground. I can even actually, I don't know if I have it handy, but I can show you pictures of what happened to it too. If you give me a couple of minutes, I can dig one up. But the vehicle actually managed to take a picture of what happened to the descent stage, and we can actually see from space as well. Sorry, let me see if I can find the right pictures and can still share them. Give me 1 second here. Again, I still have to figure out Zoom. Share that screen.
So it crashes, but does it have any, so it just crashes?
Yep, that's right. So let's see. Here's a picture that was taken shortly after landing. Hopefully you're seeing that with a portion of the image contrast stretched here. This is looking back toward the delta, and you can kind of see this white cloud here. That's what's left of the descent stage at impact with the ground. So we don't try to use it again. We just try to get it out of there. We can actually see, do I have that picture of what happened to the descent stage from space, from Mars Reconnaissance Orbiter a little later. There's the splatter of the descent stage on the surface of Mars.
Oh. So I know the purpose is to get it out of the way, but I guess it's controlled just to get away. It doesn't have any, you don't guide it to explode anywhere, or just
it's attempting to fly a attitude profile to get it to about the distance that we send it to. We send it either forward or backward from the rover, depending on which way the rover azimuth was at touchdown. Here's a picture, kind of the zoomed out version from the Mars Reconnaissance Orbiter high-rise imager, showing where everything went. So here's Perseverance down here. The heat shield ended up downrange. The descent stage ended up to the northwest, as did the parachute and back shell.
Okay. Also, I'm also kind of curious. I know the person asked right before you about the China lander. I guess what comes to mind when I hear that, I know that JPL has a lot of precautions, making sure that the lander's clean, because they don't want to contaminate Mars. So so what's coming to my mind, with another lander up there from China, do do we have any say? Like, can they contaminate Mars? I guess that's what I'm thinking. Like, do we have any? We have no.
I mean, I don't know if China is party to the international agreements regarding planetary protection. I don't have particular knowledge of that. That being said, right, they're pretty far from the parts of Mars that we're on. Although Mars is quite a bit of a smaller planet, right? It has, given no oceans, basically the same amount of landmass as Earth. So there's still a lot of Mars to explore for us all.
Okay. Well, thank you so much. That's all I have to say.
Okay, next question. Oh, okay, Jake, Mr. Pinheiro, I think you have another question. Go ahead.
Yes, thank you. During your presentation, you showed a couple of images from the TRN system with the correct and incorrect landmark identifications kind of denoted on those images. And you may have gone over this during the talk and I just missed it, but were those, identification of those being correct or incorrect, was that done after the fact or was that done by the system as it was navigating?
It was done by the system as it was navigating. So those, you saw a couple different colors that weren't green. Reds were incorrect landmark matches, but the other guys that you saw in there were actually ones. We had so many landmark matches that after 100 we start throwing them out. So we just throw out the lower quality ones.
Okay, so the system itself, it identifies something as a landmark match, but then it can further identify whether it was correct about that or not, basically?
That's right.
Okay. All right, thank you.
Okay, this question from Pankaj. Pankaj, speak out.
Yeah. Well, my question is, would the geopolitics be at play on Mars? Or in other words, would the Zhurong and the Perseverance, is there any plan to communicate with Zhurong?
We're nowhere near each other with the Chinese rover and the Perseverance are nowhere near each other. So I don't think that's really in the cards.
Okay, thank you.
Okay, next, Byron. Ms. Lowry.
I think I see his question in the Q&A. Okay, he asked, will you be looking to further reduce the landing ellipse on future missions? How much accuracy would be beneficial in retrieval missions for the future? So this is a great question and actually very, very astute because we are looking to go further, right? If with the terrain relative navigation system, with the lander vision system, we accurately identified where we were to pretty good accuracy. The only thing that prevented us from flying to a specific point on Mars, as opposed to just flying to a safe spot nearby, was the amount of fuel that we had. I don't know if I mentioned this, but we actually flew the dynamic test model descent stage that was built for MSL for Curiosity. We dusted that off and then turned it into a flight vehicle. So we were constrained to the amount of fuel that the descent stage could fly, about 400 kilos of hydrazine or so. So the only thing preventing us from doing what we call pinpoint landing or flying to a particular place on Mars with an accuracy of, in the end, on the order of tens of meters, is the amount of fuel that we put on board. So we are looking to do that for the next mission, for the sample retrieval mission, the lander mission, that'll go and pick up those samples and put them in Mars orbit. To reduce the amount of time that we spend on the ground and to get those samples back faster, we are looking at putting more fuel on board so that we can fly right to where we want to land, as opposed to just landing somewhere nearby where we happen to do backshell separation. So good question.
Okay, great. Next question is from Mr. Sin, Jaspreet Sin. Mr. Sin, do you want to speak out? Well, I think he typed his question in the Q&A.
Yeah, I can read it here. He said, what would your advice be for someone starting their aerospace career and keen to work as an EDL engineer? Competencies, skills required, specialist versus generalist. This is kind of a mealy mouth question, but the answer is it really takes people, all sorts of people, to do this. I mean, the fun thing about entry, descent, and landing is that you end up using all parts of the spacecraft and touching everything. So we need people who do everything, right? Whether it's propulsion or mechanisms or flight software or avionics or radars or IMU, whatever kinds of navigation control, you name it, we use it during entry, descent, and landing. So there are many different ways to be a part of the solution, whether it's in those areas or being more of a generalist or a systems engineer, trying to work all that. And of course, you don't even have to really be technical. I mean, we need procurement people and business folks and all sorts of other folks to make sure that that we can get to do this. So it really takes all types. So there are many different ways to come at that.
Yeah, you see, he posed another question about Sky Crane.
Oh, yeah. Okay. So the Sky Crane is inspiring and now proven to be an effective solution to the Mars EDL mission. What challenges could drive the team to think of the next solution? I mean, beyond the Sky Crane. Good question. I mean, I think, you know, one of the big things that we're taking advantage of using the Sky Crane is the fact that we're delivering a large rover, a rover that already has a mobility system designed to interact with the surface of Mars. So if you don't have that, the Sky Crane becomes a little less attractive. And I think we might see that going forward, right? If the sample retrieval lander, which I don't think is going to be a big rover, is more likely to be a lander itself, may go away from a Sky Crane system because it doesn't already have that kind of built-in landing gear from having a big high clearance rover available to it to use as a touchdown system.
Okay, I think there is another question from anonymous attendee. Can you see it? Can you see it?
Yeah. Yes. How was the EDL data sent back to Earth? Was it sent real time or stored and then dumped to go to a relay first? Yeah, good question. So there's a couple different ways to get the EDL data back. To make sure that we get some amount of data back, especially to be able to reconstruct a fault if something were to happen during entry, descent, and landing. We have two ways of getting things back kind of in real time or near real time. One is direct to Earth with X-band tones. So kind of we have these tone system where we can essentially play like a 256 key keyboard where we can play a tone for about 10 seconds and then play the next tone for another 10 seconds or so. So you can think of that as a really low rate way to get data back. But that X-band system is pretty good at getting things all the way to, from Earth, just at a very slow rate from Mars to Earth. The downside being for a place like Jezero at the time we happened to land, that Earth set slightly before touchdown. So at the Jezero crater site, so we couldn't actually maintain that X-band tone communication all the way through touchdown. Second, the rover is sending out an 8 kilobit stream of telemetry to whoever's listening. In this case, orbiters flying overhead, the Mars Reconnaissance Orbiter and MAVEN. We actually modified the Mars Reconnaissance Orbiter to be able to relay that stream of that 8 kilobit stream of telemetry to Earth in near real time. So that's what you were seeing us taking a lot of look at with the combination of those tones plus that 8 kilobit stream during landing day. And of course, after a successful landing, we have the ability to play back all the high rate recorded telemetry that the vehicle has after touchdown. So we've gotten most of that data back by relay as well from ground passes. As the rover has been doing other things too, we've been sending back EDL data and getting all our high rate IMU and all those pictures post landing.
I think Patrick, Mr. Kranczak has something to say. Patrick, go ahead.
Can you hear me?
Yeah.
Yeah. So what about the Phillies logo on your home screen? I love that. I'm from the Northeast, and my wife's a huge Philadelphia Phillies fan. Sorry, they beat the Dodgers occasionally.
Yeah, I'm from the Philadelphia area originally too.
The only comment, if you're referring to, is the don't forget the safety and mission assurance people.
Oh,
when
yes.
You talk about the needed personnel. I know you think about them every day.
I do actually. Sat close to them, and all sorts of interaction with safety and mission assurance folks. So it's been they're a big part of the mission success as well.
Yeah, again, thank you for a super presentation today. This kind of even personal remotely, it's a huge thing. I'm a new member to AIAA, and this is a huge resource, and your time tonight's much appreciated.
Thanks.
All right, folks, if no more question, I think that's thank Mr. Al Chain for this wonderful presentation. It's truly amazing, and this is really the month for perseverance. So really amazing, highly appreciate. So Jeff, do you want to say something to conclude?
Well, thanks to everybody, and especially you, Ken, for organizing yet another fantastic event.
Oh, great pleasure. I'm so excited. There's what Al is doing, has been is really amazing. And he has been appearing on multiple JPL videos. I've been following those, so you can see the real person. That's really amazing. So really great. It's a great. And he gave he was in the event when you were chair in 2013. So it was really amazing. He came back. This is your home. This is your home. Come back.
I do recall meeting him before, and it's good to see him again.
Yeah.
Yeah. We're open arm. This is your family, your home. So welcome anything you need to us anytime.
I appreciate that.
Yeah. Thank you so much. All right. Thank you, folks. You know, it's a great evening. This is truly amazing. So really appreciate you with us this evening. So we'll also post some article next month about this membership anniversary. So please stay tuned, and we'll also try to post this some short, a few words or screenshots for Al's presentation. And if anybody is willing to volunteer for writing an article for this event, that would be wonderful. Please contact us. Yeah, once again, thank you so much. Welcome, and you know, thank you for joining us, and I look forward to seeing you next time. A good night, and a good weekend. Have a good day.
You too, Ken.
Thank you.
Thank you.
Thank you. Thank you.